September 7th, 1940, London burns. 430 people lie dead in the streets. 1,600 more are wounded. And this is just the first night. For the next 57 consecutive nights, German bombers would return. Every single night, dropping hundreds of tons of high explosives and incendiary bombs on sleeping families. The Luftwaffe owned the night sky, and Britain was helpless to stop them. But in a university laboratory in Birmingham, 2 engineers were working on something the Luftwaffe command would have dismissed as fantasy. A device so small it could fit in a briefcase, yet so powerful it would transform the entire war. The Germans called it impossible. British commanders called it crazy. But by 1941, this little device had turned German bomber crews from predators into prey. Within months, the Blitz simply stopped. The Luftwaffe gave up. This is the story of how a copper disc with holes drilled in it saved Britain from invasion and changed warfare forever. This is the story of the cavity magnetron and the night the darkness stopped protecting the enemy. Picture this. You're a German bomber pilot in late 1940. You take off from occupied France just after sunset. Your Heinkel He-111 carries 2 tons of high-explosive bombs. Your target is London, 200 miles away, across the English Channel. You're not worried. You're actually excited. This is going to be easy. Why? Because you own the night. The RAF's day fighters, those legendary Spitfires and Hurricanes that barely held off the Luftwaffe during the Battle of Britain, they're useless after dark. They can't see you. They can fly right past you in the darkness and never know you're there. The night makes you invisible. Sure, the British have searchlights. They wave around in the darkness like blind men groping for a light switch. Sometimes they get lucky and catch someone in the beam. But mostly, they're just wasting electricity. Anti-aircraft guns fire randomly into the darkness, hoping for a lucky hit. The odds are in your favor. You cruise over the English Channel at 15,000 feet, engines humming steadily. Below you, darkness. Around you, darkness. You're a ghost, untouchable. 2 hours later, you see it. The Thames River snaking through London, reflecting moonlight. Even with the blackout, there's enough ambient light to see the outline of the city. You can make out docks, warehouses, residential areas. You release your bombs. 2 tons of death falling toward sleeping families. You bank away, feeling the aircraft lighten as the bombs drop. In your headphones, nothing. No warnings, no enemy fighters. The British can't touch you. You land back in France. Debrief. Get some schnapps. Sleep. And the next night, you do it all again. This was the reality of the Blitz. From September 7th, 1940, through May 11th, 1941, the Luftwaffe conducted sustained bombing campaigns against British cities. London was hit 57 consecutive nights. Then they came back, again and again, whenever weather permitted. The statistics are horrifying. Over 43,000 British civilians killed. Another 139,000 injured. More than 2 million houses damaged or destroyed. In London alone, 30,000 dead. And the RAF could barely scratch them. The British had night fighters. They had Bristol Blenheims and Bristol bow fighters, fast and heavily armed. But speed and firepower are useless if you can't find the enemy. The night fighters would take off, patrol for hours, occasionally see a glint of moonlight off a bomber's fuselage, give chase, and lose it in the darkness. Frustrated pilots would land after entire nights without a single kill. In the early months of the Blitz, RAF night fighters were shooting down fewer than 6 German bombers per month. The Luftwaffe was sending over hundreds. The math was simple and terrifying. Britain couldn't stop the night raids. If this continued, British morale would collapse. Factories would be destroyed. Ports would be rubble. Eventually, invasion. The British needed a miracle. What they got was even better. They got engineering. Britain actually had a secret weapon. It was called radar, though the British initially called it RDF. Radio direction finding, to confuse German intelligence, 2640 and into 140. Britain had built a chain of radar stations along its coast called Chain Home. These massive towers could detect German aircraft 100 miles away and track them as they approached. This early warning system had been crucial during the Battle of Britain. It gave Fighter Command precious minutes to scramble fighters and position them to intercept German bombers and their fighter escorts. Chain Home was brilliant. It was also completely useless for solving the night fighter problem. Why? Because Chain Home was ground-based radar. It could tell you that enemy aircraft were approaching. It could give you their approximate location, altitude, and heading. But once your fighters were in the air, Chain Home couldn't help them actually find and intercept the enemy bombers. Think about it. You're a night fighter pilot. Ground control vectors you toward the enemy. Hostile bomber at 15,000 feet, bearing 270 degrees, 12 miles. Okay, great. You fly that direction. Now what? 12 miles is nothing for aircraft traveling at 200 miles per hour. But in the dark, 12 miles might as well be 1,200 miles. You can't see 12 miles in daylight, let alone on a moonless night. And by the time you get to where the bomber was, it's moved. It's somewhere else. Where? Good question. What British night fighters needed was airborne radar. Radar equipment compact enough to fit inside a fighter aircraft, powerful enough to detect enemy bombers at several miles range, precise enough to guide the pilot directly to the target. The problem was that radar in 1940 was huge. The Chain Home towers were 350 feet tall. The transmitters were the size of small buildings. You couldn't exactly strap that onto a Bristol Beaufighter. The fundamental issue was wavelength. Early radar systems operated at long wavelengths, measured in meters. These long-wave systems required enormous antennas to transmit and receive the signals. You needed those giant towers. To make radar compact enough for aircraft, you needed to shift to much shorter wavelengths, centimetric wavelengths, measured in centimeters instead of meters. With 10-centimeter radar, you could use antennas small enough to fit inside an aircraft's nose. But here's the problem. Generating powerful radio waves at centimetric wavelengths was considered nearly impossible in 1940. The technology didn't exist. The physics was understood theoretically, but nobody had built a practical device that could do it. Actually, that's not quite true. The British had been working on it. They had developed early airborne radar systems called AI for aircraft interception. By mid-1940, the AI Mark III was being tested on night fighters, but the AI Mark III was garbage. It operated at 1.5-meter wavelength. It was heavy, unreliable, and had terrible range. A skilled operator could sometimes detect enemy bombers at 3 to 4 miles, but often not until much closer. The displays were nearly impossible to read, showing fuzzy blobs that might be an enemy bomber, or might be ground clutter, or might be a malfunction. The AI Markwaffe, introduced in late 1940, was better. It could detect bombers at 5 miles on a good night. The Bristol Beaufighters that carried it started getting kills. In January 1941, Beaufighters shot down 4 German bombers. In March, 11. Progress, but it wasn't enough. 5-mile range was too short. The bomber had to be almost on top of you before you could detect it. And the Luftwaffe was adapting, learning to fly lower to avoid detection, changing routes, using decoys. What Britain needed was a quantum leap in radar technology. Not incremental improvement, a revolution. And in a small laboratory at the University of Birmingham, that revolution was taking shape. February 1940, University of Birmingham. 2 physicists, John Randall and Harry Boot, are staring at a problem that's been driving radar engineers insane. How do you generate powerful microwaves? Microwaves are electromagnetic waves with wavelengths between 1 meter and 1 millimeter. The sweet spot for compact radar was around 10 centimeters. At that wavelength, you could build radar sets small enough for aircraft, but still powerful enough to detect targets at useful ranges. The problem was generating those waves with enough power. Existing devices could generate microwaves, but weakly. Not nearly enough power for radar applications. Randall and Boot were working with a device called a magnetron. Magnetrons had been around since 1921, invented by Albert Hull at General Electric. The basic principle was elegant. Electrons emitted from a heated cathode would spiral through a magnetic field and, under the right conditions, generate radio waves. But conventional magnetrons were weak. They couldn't generate the power needed for radar. And here's why. The frequency of the radio waves they generated wasn't stable. It would drift, making the device useless for precision applications like radar. What Randall and Boot proposed was radical. Instead of trying to fix the conventional magnetron design, they would rebuild it from scratch using a completely different principle. Their idea was to create a resonant cavity magnetron. Here's how it worked. Take a solid copper cylinder. Drill a precise circular hole down the center for the cathode. Then, around the outside of that central hole, drill several more cavities, like chambers carved into the copper. These cavities would act as resonators, like organ pipes for radio waves. When electrons spiraled through the magnetic field in this device, they would pass by the openings of these cavities. The cavities would resonate at a specific frequency determined by their size and shape. This resonance would, in turn, organize the electron flow, making the whole system lock onto that specific frequency and generate powerful, stable microwaves at exactly the wavelength you wanted. It was brilliant in theory. But would it work? The British Air Ministry was desperate enough to let them try. They gave Randall and Boot a shoestring budget and a few months to build a prototype. What happened next shocked everyone. By February 21st, 1940, just weeks after starting, Randall and Boot had a working prototype. They turned it on and measured the output. The device generated 400 watts of continuous power at 9.8 centimeters wavelength. 400 watts doesn't sound like much. Your microwave oven probably generates 1,000 watts. But in 1940, this was extraordinary. Previous attempts at generating 10-centimeter microwaves had produced milliwatts, thousandths of a watt. Randall and Boot had just achieved 400 watts. That was thousands of times more powerful than anything that had come before. And this was just a crude prototype, thrown together in a university lab. With refinement and proper engineering, who knew how much power they could achieve? Within months, the design was improved to generate kilowatts, several thousand watts of microwave power, generated by a device smaller than a coffee can. The cavity magnetron was a revolution. But most of the British military establishment didn't understand what they had. It was too new, too radical. Convincing people that this little copper cylinder would change the war required someone with vision and authority. That person was Sir Henry Tizard. Sir Henry Tizard was a chemist and scientific advisor to the British government. He understood two things very clearly in the summer of 1940. First, Britain was going to lose the war unless something changed. The Battle of Britain was still raging. Invasion seemed imminent. Even if Britain survived the summer, the Luftwaffe's night bombing campaign was just beginning, and Britain had no effective defense. Second, Britain couldn't win alone. It needed allies. Specifically, it needed the United States. America had the industrial capacity Britain lacked. American factories could mass-produce advanced weapons. But America was neutral. The U.S. government was sympathetic to Britain, but reluctant to enter the war. Tizard had an idea. What if Britain shared its most advanced military secrets with the United States? All of them. Radar, sonar, explosives, everything. This would accomplish two things. American companies could improve and mass-produce these technologies, and the sharing of secrets would bind the two countries together, making American entry into the war more likely. Churchill approved. In August 1940, Tizard led a small technical mission to the United States. The mission included some of Britain's top scientists and engineers. One of them was Edward Bowen, a Welsh physicist who had been instrumental in developing Britain's early radar systems. Bowen packed the cavity magnetron prototypes into his briefcase. Also in that briefcase, detailed technical documents on radar systems, sonar, jet engines, explosives, and other top-secret technologies. Years later, historians would call it the most valuable cargo ever brought to our shores. The Tizard mission arrived in Washington in September 1940. They met with American military officials and scientists. The Americans were skeptical at first. The British had a reputation for being secretive, for promising much, and delivering little. Then Bowen opened his briefcase. He pulled out the cavity magnetron, this small copper device, unimpressive to look at. He explained what it could do. Some of the Americans were still skeptical. It seemed too good to be true. So they tested it. The cavity magnetron performed exactly as advertised. 10-centimeter wavelength, kilowatts of power, stable frequency. The Americans were stunned. Dr. Loomis, one of the American scientists present, later said that the 30 seconds in which the cavity magnetron was first shown was worth more than all the other discussions of the entire mission. The U.S. government immediately mobilized. They established the MIT Radiation Laboratory, known as the RAD Lab, dedicated entirely to developing radar systems using the cavity magnetron. Within months, the RAD Lab employed thousands of scientists and engineers. By the end of the war, it would have produced over 100 different radar systems, from submarine detection to bomb aiming to gun laying. But the most immediate impact was on night fighters. Using the cavity magnetron, British and American engineers rapidly developed a new generation of airborne radar. These sets would be small enough to fit in fighters, powerful enough to detect bombers at 10 miles or more, and precise enough to guide the pilot directly onto the target. Keen. British version was called AI Mark VIII. It began reaching RAF night fighter squadrons in late 1941. The Germans were about to learn what it felt like to be hunted. Let's go back to that German bomber pilot. It's now April 1941. You're flying the same route you've flown dozens of times. England at night. Easy pickings, except tonight feels different. You cross the coast at 15,000 feet. No searchlights find you. No flak comes close. So far, so good. But you can't shake the feeling that something's wrong. Unknown to you, 50 miles away, a Bristol Beaufighter has just taken off. In its nose, a new AI Mark VIII radar set. The radar operator, hunched over his display in the rear seat, is scanning. He picks you up at 12 miles. A clear contact, distinct from ground clutter. He reports to the pilot. Contact, 12 o'clock, 12 miles, slightly above. The pilot doesn't need to see you. He just follows the instructions from his radar operator. Turn right 5 degrees. Increase speed. Climbing. At 8 miles, you still don't know the Beaufighter exists. You're still invisible. Or so you think. At 5 miles, the Beaufighter pilot gets a visual. He can see your exhaust flames, faint blue glows in the darkness. He positions behind and below you in your blind spot. His 4 20mm cannons are loaded, 6 machine guns ready. At 400 yards, he opens fire. Your first indication that anything is wrong is when cannon shells start ripping through your aircraft. The port engine explodes. Shrapnel tears through the fuselage. Your dorsal gunner, he never had a chance. Never saw the fighter. Never fired a shot. You try to dive. Try to evade. But your aircraft is coming apart. You give the order to bail out. Maybe 3 of your crew make it. Maybe. You never even saw your killer. This scenario, or variations of it, played out hundreds of times in 1941 and 1942. The introduction of centimetric radar transformed night fighting from a game of chance into systematic slaughter. The statistics tell the story. In January 1941, before AI Mark VIII, RAF night fighters shot down 4 German bombers. By May 1941, as the improved AI Mark IV and early AI Mark VIII sets became available, that number jumped to 96 German bombers destroyed in a single month. By the end of May 1941, the Blitz simply stopped. The Luftwaffe called off the campaign, not because they wanted to, but because it had become unsustainable. Bomber losses were too high. Crew morale was collapsing. The Luftwaffe's night bomber force, which had terrorized British cities for 8 months, had been effectively neutralized in a matter of weeks, and the weapon that did it could fit in a briefcase. Technology alone doesn't win wars. You need people who know how to use it. The RAF's night fighter force in 1941 included some extraordinary individuals who turned radar from a technical marvel into a devastating weapon. The most famous was John Cunningham, nicknamed Cat's Eyes Cunningham. Cunningham was one of the RAF's top night fighter aces. Flying Bristol Beaufighters equipped with AI radar, he shot down 20 German aircraft, most of them at night. He became a national hero. But here's the interesting part. The British government never publicly revealed that Cunningham's success was due to radar. That was top secret, so they invented a cover story. The British Ministry of Information started spreading rumors that Cunningham's exceptional night vision was due to his diet. He ate lots of carrots. Carrots are rich in vitamin A, which is good for vision. Therefore, eating carrots gives you night vision good enough to hunt German bombers in total darkness. It was nonsense, obviously. But the German intelligence services apparently took it seriously. German night fighter pilots reportedly started eating more carrots, hoping to match the British pilots' supposedly superior vision. The real explanation was sitting in Cunningham's Beaufighter's nose. 10 inches of AI Mark VIII radar, equipment powered by a cavity magnetron. The cat's eyes myth became so widespread that British parents started telling their children to eat carrots so they could see better in the blackout. That myth persists to this day. People still believe carrots significantly improve night vision. They don't. It's World War II propaganda that took on a life of its own. But the myth served its purpose. It protected the radar secret. And that secret was Britain's most valuable military asset in 1941. Let's take a moment to understand what made the cavity magnetron so revolutionary. Because this isn't just a war story. It's an engineering story. And the engineering is beautiful. Imagine you're trying to make electrons generate radio waves. The basic principle of any radio transmitter is that you accelerate electrons back and forth, and that acceleration generates electromagnetic radiation. In conventional radio transmitters, you use electronic circuits to push electrons back and forth at the frequency you want. This works fine for low frequencies, like AM radio. But as you try to go to higher and higher frequencies, into the microwave range, this approach breaks down. Electrons have mass. They have inertia. You can't physically oscillate them fast enough to generate microwaves using conventional circuits. The magnetron solves this problem brilliantly. Start with a vacuum tube. In the center, you have a heated cathode, a wire that emits electrons when hot. Surrounding that is the anode, a copper cylinder at high positive voltage. Normally, electrons would fly straight from the cathode to the anode, attracted by the positive charge. That's just a basic vacuum tube, like in old radios. Not particularly useful, but now add a strong magnetic field, perpendicular to the tube, running from top to bottom. This magnetic field bends the path of the electrons. Instead of flying straight out, they spiral. The Lorentz force from the magnetic field curves their trajectory. Now here's where it gets clever. Remember those cavities drilled into the anode? Those cavities are resonators. Each cavity resonates at a specific frequency, determined by its size, like how a flute produces different notes depending on which holes are covered. As electrons spiral past the openings of these cavities, they interact with the electromagnetic field inside. If an electron passes by when the electric field is pointing a certain way, it gets slowed down, giving up energy to the field. If it passes by when the field is pointing the opposite way, it speeds up, taking energy from the field. This creates feedback. The resonant fields in the cavities organize the electron flow into bunches, spokes of electrons radiating out from the cathode like wheel spokes. These bunches pass by the cavity openings at exactly the right time to reinforce the resonance. The resonance grows stronger, which organizes the electrons more tightly, which strengthens the resonance further. It's a self-reinforcing system. The electrons and the resonant cavities lock together in perfect synchronization. The result is incredibly powerful, incredibly stable microwave radiation at exactly the frequency determined by the cavity size. And all of this happens automatically, just from the geometry of the device. No complex circuits, no fragile components, just copper, vacuum, magnets, and physics. The cavity magnetron was so elegant, so fundamentally sound, that the basic design is still used today. Your microwave oven has a cavity magnetron inside. The one in your kitchen probably generates 1,000 watts at 2.45 gigahertz. It's a direct descendant of the device Randall and Boot built in 1940. That's engineering that lasts. The cavity magnetron gave the Allies a decisive advantage in the radar war. But the war didn't stop there. It escalated. The Germans knew the British had improved their night defenses. They didn't know exactly how. German intelligence suspected radar, but they didn't understand how far ahead British radar technology had leaped. The Germans had their own radar systems. They had the Würzburg, a ground-based radar for controlling anti-aircraft guns and night fighters. They had the Freya for early warning. They even developed their own airborne radar for their night fighters, called Liechtenstein. But German radar technology lagged behind the British by at least a year, maybe 2 years, especially in centimetric wavelengths. Germany never developed anything comparable to the cavity magnetron. Part of this was organizational. German research was fragmented, with different services and companies competing rather than cooperating. The Luftwaffe, the Army, and the Navy each had their own radar programs that rarely shared information. Part of it was cultural. German military leadership tended to favor offensive weapons over defensive systems. Radar was seen as a defensive technology, not a war-winning weapon. This was a catastrophic miscalculation, and part of it was just bad luck. Germany did have talented radar engineers, but they were spread thin, under-resourced, and often ignored by military leadership that didn't understand what they were trying to accomplish. By 1942, the gap was obvious. British and American radar was superior in almost every respect. More powerful, more compact, more reliable, harder to jam. The Allies used this advantage ruthlessly. Centimetric radar wasn't just for night fighters. It went into coastal defense systems that could spot submarines on the surface at night. It went into bombers as H-2S radar, allowing them to navigate and bomb through clouds and darkness. It went into anti-aircraft systems, making them far more accurate. The Germans scrambled to catch up. They captured British radar equipment from shot-down aircraft and tried to reverse engineer it. But by the time they understood what the British had done, the British had moved on to even more advanced systems. The radar war was an arms race, and the Allies had lapped the competition. Let's return to the strategic picture. It's May 1941. The Luftwaffe has been bombing British cities for 8 months. Over 40,000 civilians are dead. British morale is stretched to breaking. And then, suddenly, the night raids stop. May 10, 1941, was the last major night raid of the Blitz. The Luftwaffe threw 507 bombers at London. It was one of the heaviest raids of the entire campaign. When morning came, 36 civilians were dead, and over 12,000 fires were burning across the city. And then, nothing. No raids on May 11th, or May 12th. Days stretched into weeks. The bombers didn't return. Why? The official reason was that Hitler had decided to invade the Soviet Union. Operation Barbarossa was scheduled for June 22, 1941. The Luftwaffe needed to redeploy to the east. Bomber wings were pulled from France and sent to Poland. The night blitz on Britain ended not because it had succeeded, but because resources were needed elsewhere. That's true, but it's not the whole story. The real reason the blitz ended was that it had become too costly. In the early months, the Luftwaffe could bomb British cities almost with impunity. Losses were light, but as 1941 progressed and British night defenses improved, losses mounted. In January 1941, the Luftwaffe lost 23 bombers to night fighters and accidents during raids on Britain. In February, 22. In March, 35. In April, 67. In May, the last month of the Blitz, 98 German bombers were shot down or damaged beyond repair. These numbers might not sound catastrophic, but remember, bomber crews are difficult and expensive to train. Losing 100 bombers means losing 400 to 500 trained aircrew. That's irreplaceable, and the trend was clear. British night defenses were getting more effective every month. If the Blitz had continued into the summer of 1941, losses would have been even worse. So yes, the Luftwaffe redeployed to prepare for invading Russia. But they were also relieved to have an excuse to stop doing something that was becoming a bloodbath. The cavity magnetron hadn't just made night bombing more dangerous. It had made it unsustainable. Britain had been saved, not by more fighters or guns, but by better information. Radar had turned the darkness from the Luftwaffe's ally into its enemy. The war, of course, continued. The cavity magnetron's influence extended far beyond the night skies over Britain. As the war progressed, radar technology proliferated. The Americans mass-produced radar sets using the cavity magnetron. Thousands of units were built and deployed to every theater of the war. At sea, centimetric radar revolutionized naval warfare. Warships could detect enemy vessels and aircraft at much greater ranges, day or night, in any weather. Submarines, which had relied on surfacing at night to recharge batteries, now found the night just as dangerous as day. Allied aircraft with centimetric radar could spot surfaced submarines from miles away. This contributed significantly to winning the Battle of the Atlantic. In the air, bomber crews used H-2S radar for navigation and bomb aiming. They could identify cities, rivers, coastlines through clouds and darkness. Strategic bombing became possible in any weather, robbing German industrial targets of their cloud cover protection. The Germans, meanwhile, struggled with radar throughout the war. They eventually developed centimetric radar systems, but always a year or two behind the Allies. They never caught up. The cavity magnetron had given the Allies a technological advantage they maintained until the end of the war. It was, arguably, one of the most important inventions of the entire conflict. And yet, most people have never heard of it. John Randall and Harry Boot, the men who invented it, are not household names. The cavity magnetron doesn't appear in most history textbooks. There are no statues commemorating it. Why? Perhaps because it's too technical. Perhaps because radar is invisible, its victories bloodless. A fighter pilot shooting down an enemy bomber is dramatic, visual, easy to understand. A radar operator guiding that pilot to his target with electronic signals is abstract, difficult to visualize. But make no mistake, the cavity magnetron was as important to winning World War II as any fighter plane, any tank, any bomb. It gave the Allies the ability to operate at night and in bad weather with impunity. It denied those same capabilities to the enemy. And it did this consistently, in every theater, for the entire war. There's a broader lesson here about innovation in warfare. The cavity magnetron succeeded not because it was slightly better than existing technology, but because it was radically different. Before the cavity magnetron, radar engineers were trying to incrementally improve existing designs, make the transmitters a bit more powerful, make the antennas a bit more efficient, squeeze out a few more miles of range. Randall and Boot didn't do that. They threw out the existing approach and started from first principles. They asked, what physical mechanism can generate high-power microwaves efficiently? And they came up with an answer nobody had seriously considered before. Resonant cavities coupled with magnetron-electron flow. This is a pattern you see repeatedly in technological breakthroughs. True innovations come not from optimizing existing solutions, but from reconceptualizing the problem. The Wright brothers didn't build a better balloon or glider. They invented the airplane. Steve Jobs didn't build a better flip phone. He invented the smartphone. Randall and Boot didn't build a better vacuum tube. They invented a fundamentally new way to generate microwaves. There's also a lesson about the value of basic research. Randall and Boot were university physicists, not military engineers. They were working on fundamental questions about electromagnetic resonance, not specifically trying to win the war. But when war came, their expertise was invaluable. They knew enough physics to see a path nobody else saw. Countries that invest in basic scientific research build a reservoir of expertise that can be tapped during crises. Britain's investment in physics and engineering education paid enormous dividends in World War II. So did America's. The scientists and engineers who won the Hard technological war were products of universities, of research institutions, of a culture that valued knowledge for its own sake. That investment saved Britain in 1941. It's an investment every generation needs to make. After the war, radar technology exploded into civilian applications. Air traffic control uses radar to track aircraft and prevent collisions. Weather forecasting relies on radar to track storms. Police use radar for speed enforcement. Astronomers use radar to map planets and asteroids. And of course, every kitchen has a microwave oven, a device that uses a cavity magnetron to heat food. The engineers who developed wartime radar went on to distinguished careers. Edward Bowen moved to Australia and helped establish radio astronomy there, building some of the world's most powerful radio telescopes. John Randall became a professor of natural philosophy. Harry Boot continued research on microwave technology and electron beams. The MIT Radiation Laboratory, established to exploit the cavity magnetron, became a template for later research institutions. After the war, many of its scientists went on to found companies, universities, and research labs that shaped the modern electronics industry. The technological leadership America and Britain established during World War II, built on foundations like the cavity magnetron, persisted for decades afterward. It created the electronics industry, the computer industry, the aerospace industry, all because two physicists in Birmingham drilled some holes in a copper cylinder and figured out how to make electrons dance. Let's consider an alternate history. What if Randall and Boot had failed? What if the cavity magnetron had never been invented? Or had been invented too late? The Blitz continues through 1941. British civilian casualties mount. Industrial capacity is degraded. Morale cracks. The Battle of the Atlantic goes worse for the Allies. Without centimetric radar to detect surfaced submarines, U-boats sink more merchant shipping. Britain faces starvation. Strategic bombing of Germany is less effective. Without H-2S radar, bombers can't navigate or bomb accurately in bad weather. German industrial production continues unhindered. Does Britain lose the war? Probably not. But the war lasts longer, costs more, kills more people. Or consider another possibility. What if the Germans had invented the cavity magnetron first? German night fighters with centimetric radar ravage RAF bomber command. The strategic bombing campaign becomes unsustainable. German U-boats with advanced radar dominate the Atlantic. German ground forces with superior radar-directed anti-aircraft guns make close air support nearly impossible for the Allies. Would this have changed the outcome? Possibly. At minimum, it would have made Allied victory vastly more costly. The cavity magnetron was a true war-winning technology, not in the dramatic sense of a wonder weapon that single-handedly defeats the enemy, but in the practical sense of a technology that shifts the balance decisively in favor of whoever has it. Britain had it. Germany didn't. That made all the difference. September 1940, London burns, and Britain seems helpless. May 1941, the night raids stop. The Luftwaffe has been driven from Britain's skies. 8 months. That's how long it took for a device small enough to fit in a briefcase to change the course of the war. The cavity magnetron gave British night fighters the ability to hunt German bombers with ruthless efficiency. It transformed night fighters from a forlorn hope into a devastating weapon. It turned the darkness, once the Luftwaffe's ally, into its enemy. And it did all this quietly, invisibly, through radio waves nobody could see. John Randall and Harry Boot never became famous. Most people have never heard their names. But their invention helped save Britain from invasion, helped win the Battle of the Atlantic, helped make strategic bombing possible, and helped establish the technological dominance that the Allies enjoyed for the rest of the war. The cavity magnetron was called crazy by those who didn't understand it. It was called impossible by those who lacked imagination. But it worked. And it worked so well that we still use the same basic design today, 85 years later, in devices ranging from radar systems to microwave ovens. That's the power of engineering. A good idea, properly executed, can last generations. A truly great idea can change history. 2 engineers in a university laboratory had a crazy idea about drilling holes in copper. That idea stopped the Blitz. That idea helped win the war. That idea changed everything. The next time you use your microwave oven, remember, you're using the same technology that saved Britain in 1941, the same physics that heated your coffee. This morning once guided night fighters to their targets, over the burning cities of wartime England. Engineering isn't just about building things. It's about solving problems that matter. And sometimes, just sometimes, it's about saving civilization. The cavity magnetron was called crazy. It was called impossible. It was neither. It was just brilliant.